Okay, so if we have a paper clip, right, that's about 1 gram, right? So a paper clip, here's my paper clip, is about 1 gram. Of course, depending on the size of the paper clip and the material, it most likely will not be exactly 1 gram, but it's a good reference point. And the proton, right, in our atom here, the proton, the subatomic particle, the proton, right, tiny particle, is about, right, 1.5 times 10 to the negative 24th grams. Tiny, tiny measurement. We want to know how many protons would equal the weight of 3.5 billion paper clips, right? So the first calculation is easy because 3.5 billion paper clips would weigh, they each weigh 1 gram, right? So whatever number you have, you just have 1 times that number so if you have 10 paper clips, that's 1 times 10, or 10 grams. If you have 100 paper clips, it's just 100 grams. The number of paper clips equals the number of grams. So here, 3.5 billion, that is this number, 3,500,000,000, right? That is 3.5 times 10 to the 3/69th. Right? We have this many paper clips or this many grams. Same thing. What do we want to know? Well, how many protons would we need to get that weight, right? And that's a really tough question, I think, conceptually. Like, what's going on here? It's such extreme scale. So let's model by looking at a simpler case. If I had, let's say, I don't know, a cookie, a very large cookie, right? Chocolate chips, raisins, who knows, oatmeal, mix it all in there, big cookie, and it weighs 100 grams. Okay. And let's say I had another item like, I don't know, this green stick. Maybe it's a stick of boogers or something. I don't know. This stick right here is a smaller amount. Let's say it weighs about 20 grams. Well, if I asked you how many of these booger sticks would you need to get this cookie here to equal the weight, what would you say? Well, intuitively, you probably know it's 5. But think about the calculation here. You're really dividing. The larger amount, 100, divided by 20, and that would give you 5. It would tell you you need 5 of these booger sticks to equal this cookie, or whatever it is. So the key operation here is division, and that will tell us how many protons go into this many grams. And let's set it up. So, as our last step in the calculation, we have 3.5 times 10 to the 9th grams divided by 1.5 times 10 to the negative 24th grams. So grams divided by grams cancel out. Units cancel out like numbers. 10 to the 9th divided by 10 to the negative 24th. We're dividing, same base, subtract the exponents. 9 minus negative 24. That's really 9 plus 24. That would give us 10 to the 9 plus 24 power, or 33rd power. And our last division step is here, 3.5 divided by 1.5. And again, a lot of these divisions, I think, seem intimidating, but really think of this as an equivalent fraction, right? I think it's nice to say, oh, 3.5 over 1.5. Let's scale it up. Let's multiply both by 10, or as one of my students, Nick, was doing, was doubling both of them. I thought it was cool. That would be 7 over 3. Right? There are different ways to look at this, and I think this is hard to evaluate, but these two right here at least are easier. This is the most reduced fraction, so let's use that. I know that 3 goes into 7 2 times with a remainder of 1, so it's 1, right? Third, a remainder of 1/3. So it's 2 1/3. That's what this equals. So as we go back, 2 1/3 is just 2.3 repeating. We set this up like this, and we're done. We have our answer in scientific notation. It would take 2.3 times 10 to the 33rd protons to get us a weight with that many grams. Thanks.